Welcome to the ePathshala lecture series in computer science. We are dealing with the computer architecture course. This session we will discuss about pipeline hazards. So, we will discuss about the various hazards that might occur in the pipeline. So, the previous modules we looked at the basics of pipelining, and these are the lessons that we learned from pipelining. So, pipelining does not help the latency because every instruction will have to remain in the instruction unit for the same amount of time, but it definitely helps in improving the throughput. And the pipeline rate is limited by the slowest pipeline stage. Multiple tasks basically operate simultaneously, and that leads to an improvement in throughput. And this technique of pipelining exploits parallelism among instructions in a sequential instruction stream, and the potential speed up that you can expect in a pipelined implementation ideally depends upon the number of pipeline stages. But if you have unbalanced lengths of pipeline stages, that might reduce speed up. And also the time to fill up the pipeline and time to drain the pipeline will reduce the speed up. So, in spite of having a balanced pipeline and all that, we will still have some problems in the pipeline, and that is what we are going to focus in this module. So, if you look at the limits to pipelining, that is because of the various hazards that might occur in the pipeline. These hazards are circumstances that would cause incorrect execution if you allow instructions to move through the pipeline as normally would happen. So, there are three types of hazards. The first one is a structural hazard. Structural hazards basically arise because you do not have enough resources in a pipelined implementation. And if you try to attempt to use the same hardware in multiple stages of the pipeline, it will give rise to hazards. The second hazard is what is called a data hazard. This occurs because there is dependency between instructions. The data that is produced by one instruction is to be used by the other instruction, to quote a simple case. And the third one is a control hazard, which happens because of branch and jump instructions. Normally, you know that when an instruction gets decoded, at the same time the next instruction is being fetched. But when the instruction that is being decoded is going to be a branch instruction and the control has to be transferred to some other place, you know that the next instruction may not have to be fetched, and that is what happens in a normal pipeline. This may give rise to what are called control hazards. All this we will discuss in detail as we proceed. So, the first example is for a structural hazard here. So, as you can see here, you have a load instruction followed by other instructions. A load or a store instruction, we are still using the MIPS architecture as an example architecture. So, it is a register ISA or a load store ISA where only load and store instructions are going to use access data from memory. So, the first instruction being a load instruction, it is obviously going to access the data during the memory access. So, that is for the load instruction, and the same time you have another instruction 3 being fetched. So, the load instruction is trying to access the data memory, and the new instruction that is going to be fetched is going to access the instruction memory. Now, suppose you do not have two different memories, you do not have a separate data cache and a separate instruction cache, then you have two instructions trying to access the same memory for two different purposes, and that will obviously give rise to a hazard. This type of a hazard is called a structural hazard. So, structural hazards basically arise because we do not have enough duplication of resources. So, instead of having the same memory, if we had separate memories, if we had a separate instruction cache and a separate data cache, this problem would not have occurred. So, that is an example of a structural hazard. So, you can quote many such examples. Say for example, ALU is being used for a purpose here, and you try to use the ALU for some other purpose in the same clock cycle. Then if you do not have, say for example, as part of your instruction fetch, you always have to update your program counter. So, to update your program counter, you may have to add a constant value. For example, in the case of a MIPS architecture, you will have to add 4 to the program counter. So, as part of the fetch instruction, you will have to add 4 to the program counter. As part of an execution phase, you will have to use the ALU for some other purpose. So, if you do not have a separate adder unit as part of your fetch unit, then you will land up with a structural hazard. So, these are some examples of structural hazards. So, the structural hazard has been pointed out here. And what do you do if you have to have a structural hazard? If you have a structural hazard, obviously you can't allow the instructions to access the data memory as well as the other instruction accessing it for instructions. That cannot happen. It will lead to wrong execution. So, you generate what is called a bubble. A bubble is created in the pipeline, or a stall is created in the pipeline, where instead of allowing this instruction to do an instruction fetch here, you generate a bubble there, and that bubble moves through the pipeline here, and the next clock cycle, instead of the fetch happening in this clock cycle, you find that the fetch has been pushed to the next clock cycle with a bubble of one clock cycle or a stall of one clock cycle introduced in the pipeline. So, this is yet another way of representing the activities happening in your pipeline. So, you have a load instruction, you have the subsequent instructions, you find that a stall has been introduced here. So, structural hazards, basically you know that if you have enough duplication of resources, structural hazards will not happen. So, the simplest solution to a structural hazard is stalling the pipeline as indicated. That will give rise to a low cost solution. It is a very simple option also, but obviously it increases CPI. So, every time you stall the pipeline, you are going to increase the number of clock cycles it takes for an instruction to complete, and your CPI value is going to increase, and it is normally used only for rare cases. You do not always say let the pipeline be stalled every time you have a problem. So, you always try to provide enough resources so that structural hazards can be handled. While providing enough resources for handling the structural hazards, you can either pipeline the hardware resources. So, when you pipeline the hardware resources, so even if you have only one hardware resource, you can just go in for a pipelined implementation of that hardware resource. This is useful for multi-cycle resources. It gives you good performance. Sometimes it may be complex also. The other one is go in for duplication of resources or replication of resources. This also gives good performance. Obviously, it increases the cost, and maybe the interconnect delays also may be increased. It is useful for cheap or divisible resource. So, the second type of problem that we have in the pipeline is data hazards. Now, before we actually get into data hazards, we will first of all look at what are called data dependencies. These data dependencies only can turn out to be hazards. Now, there are three types of dependencies. You have data dependencies, also called true data dependencies, name dependencies, and control dependencies. Control dependencies actually give rise to what are called control hazards, which we will take it up separately. Now, an instruction J is data dependent on instruction I if either of the following holds. Either instruction I produces a result that may be used by instruction J, or instruction J is data dependent on instruction K and instruction K is data dependent on instruction I. Now, a name dependence occurs when two instructions use the same register or a memory location. That is why it is called a name dependence, but there is actually no flow of data between the instructions associated with that name. Unlike a data dependence, a true data dependence where there is an actual flow of data, where the data produced by one instruction is being used by a subsequent instruction. In the case of a name dependence, the data is actually not being transferred between two instructions. It is just that the same registers or memory locations are being used by the two instructions. So, that is why it is called just a name dependence. Now, two types of name dependencies exist between an instruction. So, if you look at an instruction I that precedes instruction J in program order, you call an anti-dependence between instruction I and J when instruction J writes a register or a memory location that instruction I reads, and you have to preserve the original ordering. So, the first instruction has to read some data, and the second instruction, before the first instruction reads the data, if the second instruction goes and modifies that data, then the first instruction obviously will read only the updated data which is not required. That is what is called an anti-dependence. The second case is an output dependence where two instructions have the same destination register or a memory location. So, when you have two instructions I and J and both of them modifying the same register as a destination register or a memory location, and if the program order is not preserved, that is I has to write first and then J has to write next. If that order is not preserved, what will happen is J will write first followed by I writing it. So, at the end of these two operations, it will be the contents that was modified by instruction A, I, that holds in the register, which obviously is not correct. So, name dependencies, as I pointed out, both your anti-dependence and the output dependence, they are not true dependencies. It so happens that you are using the same register or you are using the same memory location. And because this is not a true data dependence, renaming can be done very easily for register operands, and this is called register renaming. It is not that renaming cannot be done for memory operands, but it is a little more difficult to handle memory operands. For registers, it is called register renaming, and register renaming can either be done statically by the compiler or dynamically it may be done by the hardware. So, the next type of dependence is a control dependence. This determines the ordering of an instruction with respect to a branch instruction, so that the instruction I is executed in correct program order. Now, two general constraints that are imposed by your control dependencies are: an instruction that is control dependent on a branch cannot be moved before the branch, so that its execution no longer depends on the branch. Similarly, an instruction that is not control dependent on the branch cannot be brought into the purview of the branch, so that the execution is controlled by the branch. You can't do both these things. So, if you do not take care of both of them, it will give rise to control dependence. Now, looking at more with respect to data dependencies and hazards. Now, all these dependencies that we looked at, the data dependencies where you may either have a true data dependence or a name dependence. Now, all these dependencies are properties of programs. So, whether these instructions come together or these instructions are separated in space, they are still dependent on each other. So, they are properties of programs, but whether they will give rise when they get implemented in a pipeline depends on the order of execution of these instructions. So, these dependencies may or may not turn out to be hazards in the pipeline depending on the order in which they get executed. So, there is a difference between dependencies and there is a difference between hazards. Dependencies are properties of programs which you cannot do anything about it, but hazards, all you have to make sure is these dependencies do not give rise to hazards when they get implemented in a program, in a pipeline. So, data hazards, we will try to look at the classification of data hazards. Data hazards can be classified as one of three types depending on the order of the read and write accesses in the instructions. You always know that you can only perform a read or a write operation on a register or a memory operand. Now, any number of reads is never a problem. Reads are not going to modify the operands. So, reads are never a problem. The problem always arises when you have writes coming into picture. So, a read and a write or a write and a read and a write and a write, all of them will give rise to problems. So, the first one is what is called a raw hazard, which is called a read after write hazard. So, the second instruction, when you talk about two instructions I and J, I coming first and J coming next, the second instruction, Jth instruction, is supposed to read its operand after the ith instruction has written into it. So, I does some operation and writes the result, and only after that J should go and read the result. If this ordering is not preserved and J tries to read it before I has written it, then it will get the wrong data, and that will give rise to what is called a read after write hazard. The second one is a write after write hazard. Now, this corresponds to an output dependence. This occurs when two instructions I and J are trying to write into the same register. If this order is not preserved, you will find that the first instruction does not do the write first and the second instruction does not do the write subsequently. Instead, the order of writes gets reversed. So, J does the write first and I does the write next. So, the write order is not being preserved. So, this will give rise to what is called a write after write hazard. Now, this may arise in the case of, for example, when you look at a short integer pipeline and a longer floating point pipeline, where even though the integer instruction was started later, it will finish first and it will write into the register file, whereas the floating point instruction, though it was started earlier, may take more number of clock cycles to finish it, so it will do a write at a later stage. And this may give, if they are writing to the same register, this will give rise to what is called a write after write hazard. The third type of hazard is what is called a write after read hazard. Here this arises because of an anti-dependence. Now in this case what happens is, the first instruction should do a read operation and only then the second instruction should modify it. Now suppose if the second instruction goes and modifies the data before the first instruction has read its operand, that will give rise to what is called a write after read hazard. So the write should happen for the second instruction after the read of the first instruction has finished. Now if this order is not preserved, it will give rise to a write war hazard. Now this occurs either when there are early writes and late reads, or when you try to reorder the execution of instructions. So these are examples of data hazards that we looked at. So read after write hazard. So you have an instruction here. So you have an add instruction here where R1 is the destination operand, and for the subsequent instruction you have R1 as one of the source operands. So this instruction has to finish first of all, write into R1, and subsequently that should be read, the updated value should be read for the source operand of the second instruction. So if this order is not preserved, if the read of the second instruction does not happen after the write of the first instruction, it will give rise to a war hazard. This is an example of a war hazard. So you have three instructions here. So the first instruction uses R1 as a source operand. The second instruction uses R1 as a source operand. The third instruction uses R1 as a source operand. So in this case what happens is, if the second instruction is executed first, if the jth instruction is executed earlier and it tries to modify R1 before the first instruction has read its operands, then you have a problem. When I tries to read the data, it has been already modified to a different data. That is called an anti-dependence between these two instructions, and if this order is not preserved, it will give rise to what is called a war hazard. The third type of dependence is an output dependence, which will give rise to a war hazard. In this case what happens is, both I and j instructions have, as you can see, have R1 as the destination operands, and if both of them have R1 as the destination operands, and if this program order is not preserved, you allow I to finish first and write into R1, and then allow j to finish and then write into R1. If this order is reversed, it will give rise to what is called a write after write hazard. Now what will happen if these hazards are allowed to prevail in the pipeline? So this is an example to show the data hazards. So I have an add instruction which modifies register R1, and as you can see, register R1 is a destination operand for all these instructions. This is an R1, this is an R1. For all these instructions, use R1 as a destination operand. Now what happens to the first instruction is, only during the fifth clock cycle R1 will write into the register file. So the data becomes available in register R1 only during the fifth clock cycle. But by that time you know that the decode of the second instruction has finished, the decode of the third instruction has finished, and the decode of the fourth instruction is also in progress simultaneously. And you know, along with the decode process, we are going to read the register operands. So if the second instruction or the third instruction tries to read the operands at this time, it is going to get wrong results. So that is an example of a data hazard which has been depicted pictorially here. So this is again another representation of the same problem. What will happen if you generate a stall? One stall itself may not be enough, though we have indicated only one stall, you will find that that stall alone is not enough. Now control hazard is when we need to find out the destination of a branch and can't fetch any new instructions until we know that destination. For example here, say for example I have a branch instruction here. So the branch gets resolved here. So you have the branch instruction here. The branch gets resolved only during the fourth clock cycle. So, only when the branch gets resolved, you actually know that during the fourth clock cycle, when the branch gets resolved, you actually know what is the destination address. And you can see that the destination address is 36, which moves on to the last instruction here. But what happens is, when the branch is getting decoded, you also go ahead and fetch the next instruction using the updated PC, which is just PC plus 4. And the next clock cycle, you fetch the third instruction, which is again PC plus 4. Now, but once the branch gets resolved, you know that these instructions that you fetched are wrong instructions. All these 3 instructions that you fetched are wrong instructions, and you should have actually fetched only this instruction. Now, that explains what is called a branch hazard. So, there is a control dependence between these 2 instructions, and because of that control dependence, it will give rise to what is called a control hazard. So, we, as part of the fetch process, you know the program counter is always updated to the next location. But if it is a branch instruction, you know that it may or may not have to execute the next instruction in sequence. So, if that is the case, whatever instructions we put here before the branch gets resolved are wasted instructions that should not have been executed. So, what do we do about that? That is what is called a control hazard. So, structural hazards, we have looked at structural hazards, we have looked at data hazards, we have looked at control hazards, definition of all this. Now, what happens in the case of a MIPS pipeline? Will these hazards be available in the MIPS pipeline, or will they not be available in the MIPS pipeline? The structural hazards, basically, you know, there is a conflict for use of a resource. But so, whatever be the architecture that you are looking at, if you do not have enough resources, then it will definitely give rise to a structural hazard. So, in the MIPS pipeline with a single memory, if you are just looking at a single memory, then load store instructions are going to use the data memory, access the data memory, and all other instructions are going to access the instruction memory for each and every fetch. So, what will happen is, when you try to execute, only when you try to execute a load or a store instruction and it overlaps with an instruction fetch of a subsequent instruction, this will give rise to a structural hazard. That was pointed out in an earlier diagram also. So, the MIPS architecture relatively gives you less of a problem with respect to this type of structural hazard, because only load and store instructions will have to have access to data memory. All other instructions are not going to access the data memory. If it had been some other type of architecture, say for example an x86 architecture, where all instructions allow memory operands, even if it is an add instruction, it can have a memory operand along with it, then what will happen is, each of these instructions may have to access data during the data memory access cycle. So, that will always get overlapped with your instruction fetch, and that will give rise to a number of structural hazards. So, it definitely does not make sense to have a unified memory when you look at such architectures. So, even in the MIPS architecture, the moment you have a unified memory, your load or store instructions will get stalled. So, the solution for that is, you will have to fetch the instruction stall and cause a pipeline bubble. Now, this pipeline data paths require separate instruction and data memories, or separate instruction and data caches. So, that is how structural hazards are handled here. Other types of structural hazards which we already pointed out, for example, the PC getting updated during instruction fetch and you needing a separate adder for that, and not using the ALU which is used for your execution cycle, is another case. So, if you do not have a separate adder during your fetch cycle, then you will eternally have a clash for your adder unit, which is not possible. So, the moment you introduce pipelining, you will have to make sure that the resources are as independent as possible for each and every pipeline stage. Otherwise, it will give rise to a number of structural hazards. And the structural hazards, remember that all these structural hazards will have to be handled at the design stage itself. Once you have designed the system, you have designed it to go in for so many adder units, you have decided to go in for so many a split memory or a unified memory and all that, you will have to live with those stalls, and you will have to make sure that you identify such problems and stall the pipeline whenever necessary. You can never go in for incorrect execution. So, as far as data hazards are concerned, raw hazards, the first one is a raw hazard. Now, raw hazards can happen in any architecture, because raw hazards are basically hazards that arise because of a true data dependence between two instructions. So, ultimately we will always try to handle all the control dependencies and the other name dependencies and leave out only raw hazards in the pipeline, and we will also look at solutions for raw hazards later on. Now, if you look at war hazards, a write after read hazard. Now, in the case of a MIPS pipeline, writes always happen in the 5th clock cycle during the write back, and reads happen in the 2nd clock cycle during the decode and the register read stage. Now, and we are not looking at out of order execution or anything so far. So, in the case of a MIPS 5-stage pipeline where we are not looking at out of order execution and all instructions take the same amount of time for execution and other operations, a write after read hazard can never happen, because writes always happen in the 5th clock cycle and reads always happen in the 2nd clock cycle, and we are not looking at out of order execution. So, war hazards cannot happen in the MIPS pipeline. Similarly, if you are looking at war hazards basically arise because two instructions try to write into the same register or a memory location, and the writes get go out of order. If you do not preserve the order of these writes, it will give rise to a war hazard. Again, in the case of your MIPS implementation, we always assume that writes happen only in the last stage, and we are not looking at other types of instructions here. We are only considering, so far we have considered instructions having only one execution cycle, and we are not looking at out of order execution so far. So, as long as all instructions take only one execution cycle and we are not looking at out of order execution, write after write hazards also cannot happen in your MIPS pipeline. Now, control hazards obviously can happen in any pipeline, because you know that branch instructions are very common. At least about 30% of the instructions are normally branch instructions. And so, in the case of your MIPS pipeline also control hazards can happen. Now, the penalty, the amount of penalty for your control hazards depends on when your branch gets resolved. So, when you are talking about your branch getting resolved, there are two things that you will have to resolve. One is finding out the branch target address. The second one is for conditional branches, identifying and evaluating the condition. So, the condition has to be evaluated and you will have to identify the branch target address. So, if these two operations get done early in the pipeline, the penalty can be reduced. So, in the case of a MIPS architecture, we assume that the branch gets resolved in the 4th clock cycle. After the execution phase, the condition gets evaluated and you find out calculate the target address, and during the 4th clock cycle you update the PC. So, instead of doing it there, if you try to do a more aggressive implementation of resolving the branch say in the 2nd clock cycle or the 3rd clock cycle, the branch penalty will reduce. So, in order to do a more aggressive implementation, you will have to bring in, say for example, if you do not want to calculate the target address in the execution cycle, and if you want to do it in the 2nd clock cycle itself, then an exclusive adder will have to be brought in there to calculate the target address. So, such changes will have to be brought into your pipeline, so that you are able to evaluate the branch earlier and resolve the branch earlier. Now, looking at the speed up equation for pipelining, the general speed up equation for pipelining is, if you look at a CPI pipeline, you have an ideal CPI value. Ideal CPI value you know is always 1, plus if you have any stalls, all the average stall cycles per instruction will have to be added to your ideal CPI value. And the speed up is given by ideal CPI into pipeline depth divided by ideal CPI plus all the pipeline stalls that happen to your CPI into your clock cycle time pipeline divided by clock cycle time pipeline. For simple RISC machines, the CPI value is equal to 1. So, if you substitute a value of 1 here, it becomes pipeline depth divided by 1 plus pipeline stall CPI. So, if both these are the same, cycle time unpipelined and cycle time pipelined are the same, you find that speed up is equal to the pipeline depth divided by 1 plus pipeline stalls. So, ideally when you do not have any stalls occurring in your pipeline, then you know ideally the speed up is equal to the pipeline depth. So, now use this pipeline Speedup and try to look at an example here. So, we want to compare the performance of two machines and we want to find out which machine is faster. So, one machine looks at a dual ported memory so that there are no memory stalls. So, you can handle a data fetch and an instruction fetch simultaneously. The second is a single ported memory, but its pipelined implementation has a 1.0 time faster clock rate. Now, if you substitute these values here in your speedup equation, you just substitute those values assuming that 40% of the instructions are load instructions. So, only 40% of the instructions are going to give you a problem with respect to a structural hazard. So, just plug in those values here and you find out that machine A is 1.33 times faster than machine B. So, to summarize what we have looked at this module is, we know that pipelining is nothing but an overlapped execution of instructions which does not improve your latency, but improves the throughput. And in order to get an ideal speedup, we will always have to look at balanced stages. Those are the basics, but in spite of having a balanced pipeline and all that, you still will have to handle a number of problems in the pipeline which are referred to as hazards. And these hazards limit the performance of a pipeline, and there are basically three types of hazards which we have looked at. One is a structural hazard, which obviously needs more hardware resources, and these will have to be resolved during the design stage itself. The second hazard is a data hazard, which may be because of true data dependencies or may be because of name dependencies. Name dependencies can be resolved by register renaming, and data hazard, the true data dependencies, we look at solutions in the next module. Similarly, control hazards are caused by control dependencies, and these control hazards are very common in any architecture because about 30% of the instructions are control instructions, and we definitely have to have solutions to handle control hazards. We look at more of these in the next module. Thank you.